Hi, I'm going to talk about the paper Deep Scaling today. Deep Scaling microservices autoscaling for stable CPU utilization in large-scale cloud systems. So this paper has been presented by a bunch of researchers from different universities and a group from Ant Research. Uh, and they want to talk about how microservice autoscaling can be improved in a certain way. Uh, so I'll just go through what the problem is that they're trying to address, what past research and solutions have they talked about and why they did not work. What are they suggesting they should do or we should start doing, and then go ahead with how they have implemented it, tested it, and then conclude. So it starts from this basic requirement which all of the systems and microservices have today. Um, any service we use, suppose let's consider Netflix. Today, if we pay for the subscription, there are some things we expect we get out of it. And that is something we call the service level agreement. It is the agreement you make with your clients or users because we've paid for that service, right? The next step is the co- company in itself. Netflix would have some objectives which they need to meet that agreement. So they set a certain number of objectives such that they can provide us a stable service with, say, some percentage of uptime and some basic speed or throughput in their services, etc. And to do that, they have some service level indicators, which are like real numbers, which they help them check what is the performance and how well are they able to achieve the service level objectives. So in this paper, we talk about how cloud service providers, in order to achieve these service level objectives, are over provisioning CPUs and underutilizing those allocated resources. So as a whole, every cloud service provider wants that whatever SLO has been defined, are being defined, are met. They do not want to have complaints there. And in order to meet those requirements today, with the increasing number of microservices and increasing number of scale requirement, they over provision CPUs and underutilize those resources because they do not want to miss out on the SLO. To the cloud auto scaling scenario, it is achieved in two ways. There are two main kind of ways to go about cloud auto scaling. One is learning based and another is rule based. A rule based approach is something where you set a threshold that say if I have 10 instances and each of these instances reach 70% of their capacity, add 10 more instances in my cloud system. This kind of a rule based system requires expert knowledge, and it is very labor intensive when you're talking about large clusters, because you need to know what are the factors to think about when you're scaling up or scaling out. And for each of the different kind of clusters you have in your organization, you need to do it separately. The another approach of going about it is learning based approach, where it has been talked about in research, but and it has been proven to be effective, but research never considers or hardly considers resource wastage. uh, there's a lot of service workload variation in different kind of services, and researchers do not account for this in the prior solutions. So going ahead, the problems they think are there between in the past solutions. The first is the complex interaction between services. Today, microservice architectures have different kind of services. All of these services behave differently. On the right, I have an image which gives a general, say, Uber-like example, and different parts of these different services have different hit history and different kind of workload which they get from the user versus what they get from the server. There are complex interactions between these services. Payment gateways probably not called in as many times, but passenger management and driver management are called in much more frequently. Uh, there is variety in how these components utilize the CPU. Again, the passenger will refresh a bunch of times. They will try to book a cab and things like that. And those processes will need you to do more computation when you're mapping them to the best possible match of a driver, versus when you're just running the payment channel or just notifying the passenger that, hey, your driver is here. These services do not really need as much CPU utilization. So there is a lot of variety in how these components utilize CPU. And there is a complex relationship between the service pods and CPU utilization. It is not a simple one-on-one mapping where you can say that, hey, these are the services which need more CPU and these are the services which do not need more CPU, because these things can change dynamically based on say events, based on different kinds of locations. Some areas may have very few drivers and passengers, and that's why these components might not be heavy. Some may have many drivers and passengers, making the match process much more CPU intensive. So the workload characterization is one of the most difficult parts. And keeping in mind all of these problems, they work on, they break the problem down into three parts. One is forecasting workload. It is not sufficient to make a linear prediction or simple regression to forecast how much workload you're going to get. Another is characterizing the workload. Uh, a lot of solutions only account for the number of RPCs that are being exchanged between these microservices, which is again insufficient for us to characterize our workload. And the third would be the prediction of resources. There is a complex relation between service pods and CPUs, like we discussed. And all of this is difficult to predict when you need more resources and how much of it when utilization is at its peak. Say we have an e-commerce website like Amazon or Alibaba, and on their days, sale days and Black Fridays and stuff, their utilization is at its peak. So that is when it is even more difficult to predict what are the resources and how much should you scale to know if you're actually meeting the requirement and at the same time not wasting resources. So they design a three-phase solution. The first part of the solution is the workload forecaster. The second part is CPU utilization estimator. And the third part is scale decider. Very simply, the first part tells you, sort of tries to work with the workload characteristics it has and forecast what is the kind of workload you can expect in different services. The second part estimates the CPU utilization, and using these two, it then decides the scale and predicts and tells you how much you should actually scale and when. So workload forecaster. So this is where all the heavy math stuff and I would say machine learning comes in. They use a spatial temporal graph neural network to forecast future metrics instead of, say, a linear regression or a simple regression. For this, they monitor 7 commonly used consumption metrics, RPC in and RPC out. That is how many RPC requests each of these services are receiving and how many are they calling, message publication and message subscriptions, DB access, page views, and file IO counts. Keeping in mind monitoring all of these 7, they predict what is the workload, and they've seen this forecasting to be very well received in comparison to state-of-the-art forecasters like True Value, Transformer, and NBeats. And even when there are significant changes to the workloads and there are bursts, we still see that deep scaling can keep a good estimate with respect to the true value compared to transformer and NBeats. So on the right, the graphs are for the 4 out of the 7 metrics. That's RPC in, RPC out, DB access, and page views. And the red line is deep scaling. So we see the red line is very close to the dotted black, which is the true value. So deep scaling has done a pretty decent job with that. The second part is the CPU utilization estimator. So this is a single model to estimate CPU utilization for all microservices. So there are some features it tries to take account of. The first is instance count, the number of instances of pods or pods you need for each microservices. Then there is the service ID to identify this microservice, and a timestamp which they use to collect the workload metrics and forecast accordingly. So they use a feature embedding method, which is a combination of the workload metric vectors, a time series of the workload metric as a vector, and the auxiliary features as a scalar, and try to predict again the CPU utilization and estimate it. So we again see that deep scaling does a very decent job in comparison to the true value. The third and final part is the auto scaling decision making. So where you find the recommend number of instances for a microservice. For this, they use a reinforcement learning model. The environment is a variation of CPU utilization during the running of a microservice, and the observer is the CPU utilization estimation model. So in reinforcement learning, you have an environment, you have an environment observer, and then you have the state space and the active space. So they use this environment, create a state space, and keep running it until they find an active, until they're able to establish estimation of the number of instances they need for this microservice. So this particular model, they experiment and evaluate this on the AND microservices of AND group. They categorize 3,000 different microservices and use 58 of them. The microservices have a good distribution. That is, a lot of them are RPC request intensive, a lot of them are DB access intensive, and a lot of them are file IO access intensive. The nature of these microservices, most of them are providing a high, it is to provide a high availability online payment platform, and services in this are usually accessed much more than 500, at least about 500 million times every day. All of these experiments they've spoken about has been run on a Linux server, the given specifications. So moving ahead. They compare their approach to state-of-the-art autoscaling mechanisms and rule-based autoscaling. For autoscaling, they refer to workload-based autopilot, which uses which builds the optimal resource configuration by using historical time window that matches best with the current time window. So it does sort of like a prediction based on just how the last time window was, say, last year or yesterday, and then predicts the resource configuration just based on that. Then there is an SLO based autoscaling firm. So firm is a RL based autoscaling approach, which is and it learns to adjust resources based on the feedback. It finds services with abnormal response times through anomaly detection, and then adjusts those multiple services for service through RL iterations. So it just tries to make the response times uh, decent and uniform. And finally, rule-based as the baseline, which dynamically scales the instance number of a microservice based on the performance metrics and experts rules. So in most of the experiments, they speak about 5 microservices, A1, A2, A3, A4, A5, which are like a chain in one of the to access one service, one feature. And A1 is a database dominated microservice, and A2 is a messaging middleware. And this is the performance they have talked about. So this is the effect of different auto-scaling approaches, autopilot, firm, and deep scaling and rule based, which we spoke about now. And the orange straight line is the SLO, which has been promised. And we see that with deep scaling, we're always about where the SLO is, and the variation is much lesser in comparison to other approaches. We're also utilizing much more CPU and using much less resources in general. So other than performance, we talk about stability. Deep scaling achieves and maintains a services utilization and targets almost target level almost across the entire day. It improves the relative CPU stability. So they have two metrics called RCS and RRU. So RCS is the stability rate, and it improves it to 24.6% compared to firm, which is another SLO-based approach. And it is much high. It provides much higher resource efficiency measured using RRU, and it's almost 14% better than firm. So, in conclusion, the approach takes care of multiple caveats. It takes care of multiple angles of autoscaling and works for the given set of microservices which are provided from Ant Group. It is currently deployed in the production environment of Ant Group and saves considerable resources per day in practice. Its performance is heavily dependent on workload forecasting. So they talk about a part where they remove the workload forecasting layer, and they say that in that case, deep scaling cannot cope. When auto scaling with real-time workloads, the instance controller is not able to predict the right number of instances, and it ends up taking a lot of time in starting a new service. So this approach is only useful if we have prior data and if we are able to store some prior information about this. Without workload forecasting, this does not work. So considering how dynamic the request, how dynamic and real-time services are becoming, I am not very, this one question I have from the paper is, how would this actually scale in terms of real-time workloads and in terms of when the services are more dynamic and we cannot properly use a workload forecaster to predict the instances and take the benefit out of them. So that is it.